Hello, and welcome to the Current Science and Technology podcast from the Museum of Science in Boston. I'm your host, Susan Heilman, and every week we bring you interviews with guest researchers and our museum staff covering science and technology in depth. It's Nano Days once again, and I have one of our guest speakers, Dr. Pablo Jarillo-Herrero, a physicist from MIT, who's going to be talking to us today about 2D materials. Hi, Pablo. Thanks for joining me.
Hi, how are you?
I'm good, and I'm really interested to know more about why you're studying two-dimensional materials. Everything, it seems, is leaning towards three-dimensional. People want to see three-dimensional movies and three-dimensional TVs and three-dimensional printing. Is two-dimensional going backwards?
So actually, for physicists, three-dimensional is kind of old-fashioned, and 2D is the way forward, actually. This is a bit different from movies and 3D printers.
It is. So, I mean, I guess that could make sense if we live in a three-dimensional world, so it's maybe easier to study things in three dimensions.
Yeah.
So it's harder to then go to a two-dimensional world.
Yes. I mean, you have to imagine that, indeed, scientists, for centuries have been studying objects which are three-dimensional because that's what you mostly encounter. Mm-hmm. It took actually quite some effort to realize that you could go to two-dimensional materials or two-dimensional objects, and they do have very, very different properties from three-dimensional objects. And this is something that we're learning now.
So probably the most famous two-dimensional object we've mentioned on our podcast before, people may have heard of graphene.
Yeah.
Can you tell us a little bit about graphene and how it was discovered?
Yes. So graphene is a single sheet of carbon atoms. One can think about it as a single sheet of graphite, which is a three-dimensional material.
So graphite being basically the quote, lead
exactly.
in your pencil.
Graphite is what you find at the tip of your pencil. And when you write with graphite, what you're doing is you're essentially, if you think of graphite as a deck of cards, you're spreading those cards on the piece of paper. And those are the sheets that you're spreading of graphite onto the piece of paper. And these sheets are actually many, many pieces of graphene sort of put together and being spread on the paper.
Okay, so you're still not getting graphene when you write with a pencil.
No, although probably here and there are some individual pieces of graphene, but for the most part, it's very thin graphite.
And so in order to isolate it, you can't just write on a piece of paper and say, oh, there's some graphene for me to study. So how would you even get to graphene?
So the way graphene was first isolated, and it's still by and large the way we do it today, is by using Scotch tape. You take exactly. You take a graphite crystal and a piece of Scotch tape, and with this piece of Scotch tape, you can split the graphite into many pieces. And now, as you split this graphite into many pieces, because Scotch is sticky, so if you put both sides of the tape on both sides of the graphite, and then you pull, you split it. When you do this, occasionally there's some layers of graphene which are sort of sticking out from the graphite, a little bit left hanging there. So if you now press the Scotch tape with these pieces of graphite, which have hanging pieces of graphene in it, onto a substrate, and then you remove the tape, it so happens that we find pieces of graphene stuck on the substrate. And this can be pretty large, and that's the way it was isolated first. So it was very simple, very creative, and it's amazing that actually people got to do this.
Why did they want to isolate it? Because they knew it was there? I know now that graphene has some amazing properties to it. Did they know that before they isolated it?
So actually, to be honest, this was something which was very courageous because two-dimensional materials, in principle, there's a theorem in physics that says that they should not exist.
Oh.
So people thought of them theoretically, but never thought they would be able to measure them or to isolate them. And it just took sort of people very brave who disregard theorems in physics to actually isolate them. There were theoretical predictions, so there was some insight that if you would be able to isolate it, which is impossible, but if you could, then graphene would have extraordinary properties. And then once it was isolated, we started to confirm some of the properties and discover new ones.
So that is pretty groundbreaking when they basically did the impossible. They had a 2D
Exactly.
object, and I believe they won the Nobel Prize
Yes,
for doing that.
yes,
But it was beyond more than just proof of principle. Like, hey, look at us. We made 2D objects. Let's move on from there. They were then able to start proving the theoretical properties it should have.
yes, indeed. So graphene is a very unusual and special material in many respects. It is the best conductor of electricity in the world. It's also the best conductor of heat in the world.
Oh.
It is also the strongest materials in the universe. At the same time, it's the lightest material. It's only 1 atom thick and it's made of carbon, which is a very light material. It's, despite being the strongest, it's also very flexible because it's only 1 atom thick, and it's almost completely transparent because, again, it's only 1 atom thick. So it has all of these very unusual electronic, optical, and mechanical properties, which, some of them we've already discovered, some of them we're still discovering, to this day.
And so that's where your research comes in. You're working with graphene itself.
Yes, I do experiments on graphene and other 2D materials also, yes.
So you mentioned other 2D materials. So before it was considered impossible to have any 2D materials. Then they discovered graphene, they isolated graphene. I guess that then paved the way to look for, can they find other two-dimensional materials? And what did they find?
Exactly. So soon after the isolation of graphene, people realized that there are many materials which are layered, similar to graphite, and therefore it is probably possible to isolate individual monolayers of these other materials, similar to the way we isolated graphene, just using Scotch tape. So
they use Scotch tape.
exactly. We started to Scotch tape all kinds of materials so that we could isolate different 2D materials. And that's fascinating because these other materials also have very unusual properties. So now we have a complete slew of new two-dimensional materials whose properties we're studying.
So what are some of these other two-dimensional objects? I mean, the lead in the pencil, the graphite, that's a very common element we all know. What are some of the other objects?
Yeah, so it turned out that in order to get some sort of guidance to where to look, people started to look at lubricants, because materials which are lubricants are typically layered materials.
Oh, that makes sense.
So one of the materials that people looked at is hexagonal boron nitride. So it's very similar to graphene in structure. It's also a honeycomb lattice, or like chicken wire. But instead of having carbon atoms everywhere in the hexagon, you have alternating boron and nitrogen atoms. That's why it's called boron nitride.
Okay.
So that was one of them. There's another one, for example, which is called molybdenum disulfide. That's actually a very common lubricant. If you go to a hardware shop and look for a lubricant, it's likely going to be either graphite or molybdenum disulfide. Oh. And again, this material, the material that I mentioned before, hexagonal boron nitride, is actually an insulator. It doesn't conduct electricity at all.
In the three-dimensional form or the two-dimensional?
They're both insulators.
Okay.
On the other hand, this molybdenum disulfide that I just mentioned, it is a semiconductor. It's not a metal, it's not an insulator, it's a semiconductor similar to silicon. So it can be used for many applications where we currently use semiconductors, including transistors, optoelectronics, light-emitting diodes, and many other things, solar cells. So we have now very different 2D materials with different physical characteristics and behaviors. And it's just amazing that we have now all of these 2D materials, and their properties often vary very significantly from their 3D bulk counterparts.
Sounds like it, yeah.
Yes.
So you do something really interesting with these two-dimensional materials. I believe you are making them three-dimensional again. Is that how you would describe it?
Exactly. It is very interesting that we went from 3D to 2D. We saw that the properties are very special. But then what we realized is that because we have essentially what you could imagine as, we have cards from decks of cards, and we have different types of decks of cards. Now we can take a card from each deck and make a totally new deck that didn't exist in nature before by placing them on top of each other. So we can take literally these 2D materials, these 2D sheets, which are just 1 atom thick, and we can just stack them on top of each other one by one to make any material, any new material combination that we want, which has properties different from any 3D material and from any 2D material, because we're restacking them in with whatever order that we want of new 2D materials. So it's really fascinating because we have millions and millions of possible combinations now of 3D materials made of new 2D materials, one layer at a time.
What are some of the things that these new 3D materials could do? I mean, if you're taking a conductor and an insulator, and a conductor and an insulator, so how does that material act?
Well, let me give you an example. We can take a piece of graphene, a single sheet of graphene, and put it on top of a single sheet of hexagonal boron nitride.
That's the insulator.
Yes.
Okay.
So graphene is the best conductor in the world. Hexagonal boron nitride is the best insulator in the world. And now, if we put them on top of each other, something that I haven't told you yet is that actually we can put them with different angles with respect to each other. So we can also rotate one sheet with respect to the other. It's something that it's impossible to do in general with other materials that we were growing or manufacturing. So when we put one sheet on top of the other, we can have, again, the best conductor in the world, even better actually than if the hexagonal boron nitride is not there.
Oh.
Or we can turn the graphene into a semiconductor or an insulator just by rotating the angle between the two sheets. So that's something that is fascinating, and we just discovered a few years ago.
Yeah, that's amazing.
So maybe I can give you even a more weird example.
Sure,
you can
love
take
weird examples.
You can take graphene, which is the best conductor in the world, put it on top of graphene itself, which is the best conductor in the world.
I was going to ask if you can do that.
Yes, you can do that. And depending on the angle between the two graphene sheets, you can keep the best conductor in the world times 2 because you have two of them.
Right.
Or you can make a total insulator out of it. And again, this depends only on the angle between the two sheets.
Is that ever something that you could change while it's in the material? Like, could you ever have it go one after another? Like, could you move it while it's in something and be like, oh, it's a conductor, and now it's an insulator, now it's a conductor?
Yes, this is something which it's not very easy because it's like you have to imagine a little bit like having plastic wrap on the kitchen table, put another sheet of plastic wrap on top of it, and not try to rotate one with respect to the other.
Yeah, no, it's not going to work.
It turns out it's actually not quite as bad as that.
Okay.
The layers, the two graphene sheets, when you put them on top of each other, are less coupled than plastic wrap to plastic wrap.
Okay.
But it is still not easy. And we're only now beginning different groups. We're starting to understand how to do this. For now, what we mostly do is we choose one angle or another angle.
Okay.
But to change the angle so that we go from best conductor to insulator, we can only do it in relatively slow. We can't do it with a very fast knob.
Okay, so not like a switch.
Not like a switch. Although I believe we're not far from it, but not there yet.
So that would be a goal.
Yes, that's one of the things that we're working towards. Yeah.
That's pretty cool. Where could you use something like that? Would that be in a computer?
So one could possibly use this in transistors in computers, indeed. It might be that this might be more useful for several types of optoelectronic devices where it's important to control the conductivity of an element, for example, for light modulation and things like that. With many of these 2D materials and the behaviors that we observe, they're so unusual compared to our current technology and our current materials that in many cases is like this great property that we don't know yet very well what to do with because it's totally new and very different. We have to invent the technology that makes best use of these new unusual properties.
Right, and you're going to be surprised by whatever you find and kind of have to go from there. So you can't even, I guess, plan too far out.
Yes.
Because everything you do next is going to be based on what you just found.
Exactly.
So being able to predict where you might use these in the future is going to be very difficult because you really don't even know necessarily what you're going to find. But you mentioned optoelectronics as being one possible future use for it, or at least avenue to look through. What are some other places you could use some of these cool stackable turning different angle type materials?
Yeah, so maybe I'm going to mention potential applications of not just the stackable, rotatable materials, but in general of these 2D materials,
Sure.
both in monolayer or single sheet, single layer format, and also in heterostructures. So one thing that a lot of people are interested is in using these materials for flexible electronics. So, for example, because these materials are very strong, yet at the same time are so thin, they're very bendable. And because you have all the electronic properties that you need, all the electronic behaviors, the physical behaviors that you need to make electronics, you have insulators, you have semiconductors, you have conductors, then in principle you can do all of the electronics that you want in a format where you could have it flexible and you could integrate it, for example, into fabric. Like you could make clothes full of electronics.
Yeah.
These materials also turn out to be very cheap to grow in large areas. So you could also use it for large area electronics, like cover all of the windows of a building, for example, with these materials, which are almost transparent.
Right.
But they absorb enough light that they could control electronics and power electronics and sensors and displays in the windows of your building, and which could be switched on and off, for example.
Wow.
So,
that's some cool application there.
yes. So, and this is just sort of the tip of the iceberg. Many people, for example, these 2D materials, they have a very large surface to volume ratio because they're all surface, in fact.
Right.
So, if you want to make batteries or supercapacitors, this property is very good. For batteries and supercapacitors, you want to have as much
The more surface area possible.
The more surface area, the more
you can store
energy indeed in the elements that circulate in batteries. So a lot of people are also trying to use these materials for batteries and supercapacitors. So there's really a lot of we're sort of beginning to see many startups and many concepts, and people are trying to work with all these things. It's not clear yet what will be the killer application, that will be the most, for which all of these 2D materials will be better suited. And probably that killer application, we don't know about it yet.
Right. Yeah. You might not even know what it is. And sounds like you're not interested in the startup company part, but you're more of a pure physicist. You're in the lab. You want to know what these things can do.
Exactly. And in my group, we mostly investigate these 2D materials out of intellectual curiosity.
Yeah.
We want to understand their properties. We generate knowledge. We don't shy away too much from applications. We're happy also if these materials have applications.
Of course.
And then we collaborate with our engineering colleagues to develop those. But our motivation is mostly curiosity-driven. Yeah.
That's a great reason to be doing this research then. Well, I want to thank you very much for joining me here today and for telling us about how cool two-dimensional objects really are.
Thank you. Thank you for the invitation.
That's it for this week's show, but be sure to come back next time for more of the latest in science and technology. This podcast is a production of Current Science and Technology at the Museum of Science in Boston, part of the Boston community for over 175 years. For more information, visit our website at www.mos.org/CST or email us at podcast@mos.org. Thanks for listening.